It's that time of the year again. It's the Nobel Prizes.
Always charge my phone up. You never know, do you? But
again, overlooked.
Yeah, just need to check the number.
I called it. Yes, I'm feeling a bit smug about this because about 5 minutes before the announcement, I suddenly had this feeling who was going to win. And sure enough, they did, or at least they won half the prize anyway. And the other half of the prize went to a guy called Jim Peebles.
A good call to see Jim Peebles get half the Nobel Prize. He's regarded, I think, as the father of modern cosmology.
Did you put a bet on or anything?
I should have done, shouldn't I, really? Yeah. But no, I didn't. And it was literally 5 minutes before the announcement. It wasn't that clever a prediction because I certainly wasn't the only person predicting it, and they've been sort of one of the runners and riders for a number of years now, but I sort of thought it was their time. It's a slightly strange award, and actually, so the citation reads, was awarded for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos, which could be pretty much for anything, really, because that covers pretty much everything there is. But Jim Peebles is a cosmologist and is really one of the towering founding figures of modern cosmology, in that he did a lot of the work. He was part of the group that was predicting the existence of the cosmic microwave background. He did a lot of work about the growth of structure in the universe, the impact of dark matter on how structure would grow. So really, I mean, he is, if you teach a course on cosmology, in large part you're talking about his work.
The model which is fitting the data so well has his influence on every single part of it.
He is a theorist, but he's one of those theorists who actually maintains a very close link to the observation. So some of his work, he's written papers which are presenting observational data, but more in a fairly theoretical framework. So you would think of him as a theoretical astrophysicist.
He's just demonstrated that in modern cosmology, these are the key ingredients we look like we need. And he was there at the start of each one of them playing a role. So he can be, I think, properly regarded as the father of the subject and the expert.
It says it there on your board.
Oh, yes.
Father of modern cosmology.
Yeah, that's what I decided to call it. I did a tutorial today. We have a tutorial system here at Nottingham where all the first years get to have there's usually 6 in the group. I screwed up. I had to do 12 and so I thought, well, you've got to tell them about the Nobel Prize, or at least the bit I know about it.
If you were talking about Jim Peebles, you wouldn't say, he did so-and-so, because there's just so much he's contributed. So the other half of the prize was shared between Michel and Didier Queloz, and they worked on studying exoplanets. They still work on studying exoplanets, so planets outside the solar system. And it was awarded for, and let me get the exact wording here, for the discovery of an exoplanet orbiting a solar-type star. So it was really their discovery in 1995 was what kicked off the entire field of exoplanet studies.
Because like exoplanets these days are like candy, aren't they? They're like,
There are many, many thousands of them. At that point, there was only one. Actually, that's not quite true, because there were other planets, and it's interesting the way they worded the citation. It says an exoplanet orbiting a solar-type star. The first exoplanet was actually found orbiting a pulsar, a neutron star, rotating neutron star, which is a very weird system, and no one really expected to find planets around pulsars. And so it was clearly something very strange, and so although it was interesting, it was like everyone was, well, it's nothing like the solar system, so it's not really a planet in the sense that we would understand it. There were also tentative discoveries of planets orbiting giant stars that preceded the Michel and Queloz discovery. But this was really the first announcement of one which we would sort of equate with something like the solar system. So it was a solar-type star, very like the sun, with a planet in orbit around it.
Do you happen to know what star it was? It was obviously a nearby star.
It's 51 Pegasus is the star, and the planet's called 51 Pegasus b. It's about 50 light years away. It's a very ordinary star. As I say, it's a G-type star, so very like the sun. A little bit more massive, I think it's 1.1 times the mass of the sun, so a tiny bit more massive, but really almost a twin of the sun, very bog standard kind of star.
What method did they use to discover it?
So they use this radial velocity method. I mean, there are now a whole slew of methods that are used for discovering and studying exoplanets. But one of the foundational techniques, and the one that made this first discovery, was this radial velocity technique, where if you've got a star and you think of a planet in orbit around it, the sort of simple picture is the star is stationary in the middle and the planet's orbiting around. But of course, they're actually tugging each other and sort of orbiting around their mutual center of gravity. What that means is that the planet is tugging the star backwards and forwards, as well as the star tugging the planet backwards and forwards. So the star is actually oscillating. And so sometimes it's moving towards you and sometimes it's moving away from you. And by studying the spectra of the star and looking at those little dips where there are spectral lines in the star, you can see whether they're being shifted, Doppler shifted towards the red end of the spectrum or the blue end of the spectrum. So you measure that backwards and forwards wobble of the star. And that gives you a measure of the mass of the thing that's orbiting around it, as well as how rapidly it's orbiting around it by how quickly the thing oscillates backwards and forwards.
You know, that's a good method. I imagine that method had been thought of for quite a while, and all the astronomers in the world have access to telescopes and telescope time. What did these scientists do that made them able to be first? Like, what method or trick or idea did they have that made them the winners?
So there's a couple of aspects here. Firstly, people weren't really looking that hard at the time because there was no expectation that you'd actually be able to detect much. Because we had this, so if you think about what's easy to detect in this case, you want something where there's a strong gravitational pull between your planet and the star to tug it a long way.
So it's got to be a big planet.
So there's two things. You want it to be a big planet, so it's massive, so it'll tug the thing backwards and forwards. And actually you want them close together, so the pull of gravity is strong, so that the movements are bigger. And so what you'd really want is a planet like Jupiter close to the star. Now at the time we only knew about one solar system, and Jupiter in our solar system is a long way out. As is the way with scientists, you know, if you've only got one example of something, you convince yourself that that's the way the universe works. So we had all these ideas at the time, back in the 1990s and before, that actually Jupiter-like planets only existed in the outer reaches of solar systems, and things close to their stars were all little things like Mercury and Earth, which you wouldn't be able to detect. And so because of that, there wasn't really a huge expectation that we'd be able to detect this kind of effect. And what these guys actually found was something that's about half the mass of Jupiter, very close to a star. And so actually, and subsequently, of course, we found many of these hot Jupiter-like planets, so Jupiter-like planets which are close to the star. And so it turns out that actually the universe doesn't work the way we thought it did back then. And there are mechanisms where even if a big planet forms a long way out in a solar system, there are mechanisms by which it can kind of migrate inwards towards its star. So they found something that no one was really that much expecting to find, which is why there wasn't a huge rush to try and find these things. The other thing is they had some very clever instrumentation. They actually built a custom-built spectrograph that allowed them to measure very small Doppler shifts. They were down at sort of tens of meters per second that they were measuring these wobbles in these stars, which did require very good instrumentation, very stable instrumentation, where you can actually calibrate things with that kind of accuracy to really measure those very small shifts.
So you couldn't have just had like an off-the-shelf night of VLT and have found it sort of thing? Like...
You probably could now with VLT, but in the 1990s, no. You really wanted a custom-built instrument. It wasn't on that large a telescope. I think it was a 2-meter telescope. So even by then, those standards, the standards of the 1990s, it wasn't a particularly huge telescope. But it was just a very clever spectrograph, and they were looking for something that no one else was really looking for.
As an astronomer, and you were an astronomer in the 90s...
I was, yes.
Do you kick yourself and think, oh, I could have done that? That would have been like a week's work, and I could have been the one to find it.
So the interesting thing is, before their paper in the 1990s, in the 1980s, let me show you their paper. So here's their paper, published in 1995, a Jupiter mass companion to a solar type star.
Nobel Prize,
Nobel
right
Prize.
there.
And it's actually not a particularly long paper. It's not got many pretty pictures in it. A few graphs.
Not even a picture of the star.
Not even a picture. No, nothing spectacular about it at all. I mean, nice looking data. Here's the wobble backwards and forwards of the star. So sometimes it's going away from us, sometimes it's coming towards us. And you can see, so here's the scale, 50 meters per second. So there's small shifts that you're actually measuring here. So that's the wobble that they were measuring. So here's the interesting thing. That was the 1990s. In 1989, this paper came out. The Unseen Companion of Telephone Number, a Probable Brown Dwarf. And it turns out they had actually also discovered a Jupiter-like planet.
He's on there as well, there.
He's actually, Michel is on there as well. So he's one of the authors. But the primary mover of this, guy called Dave Latham, was actually in an office just over the corridor from me at the time, because I was a PhD student and he was a proper serious scientist at that point at the CFA in Boston. He wasn't very excited about this result. I mean, he was a bit excited, but he was actually, because, and again, it comes back to the fact that no one was expecting to find planets. And the reason why he didn't know that he'd found a planet, so brown dwarfs are sort of one up from planets. They're sort of failed stars. And no one was, people were expecting to find brown dwarfs because we find binary stars quite a lot of the time. And they have different mass ratios. And it wouldn't be terribly surprising if once in a while the littler one turned out to be not quite making it as a star. So people were not that surprised to be finding stars with brown dwarfs in orbit around them because they're basically just very closely related to binary stars that we know exist.
Like a failed binary.
It's one half of it's kind of failed to ignite. So one half is a star, the other half didn't quite make it. Because they weren't expecting to find planets, he convinced himself he hadn't found a planet. And the reason why there's an ambiguity, because you might think, well, you know, we know what masses brown dwarfs are, we know what masses planets are, wouldn't he have known? Turns out there's an ambiguity in this method. And the ambiguity in this method is, I kind of drew this, you know, when I was waving my hands around, I did it like that. But we don't know whether the system's like that or whether it's sort of, I can't do it that way, yeah, like that. And of course, if the planet's orbiting that way, you don't see the star is still moving, but it's being tugged in the plane of the sky. So you don't see these Doppler shifts. So this is ambiguous, and of course you can have anything in between. So actually, if you see a certain movement, it could be like, if it's, you know, you see a certain movement, it could be a relatively low mass thing that's in the plane of the sky, so we're seeing all the movement of the star. Or it could be it's almost in the a much more massive thing, and actually this thing's really jerking around all over the place, but we don't see most of the motion because most of it's in the plane of the sky rather than towards us or away from us.
You've got to get lucky. It's kind of, you need it to be punching you in the face rather than wobbling around.
To get the biggest signal, you really want to be lucky and just catch the thing edge on so you see the biggest signal. Because there's less ambiguity, you can't tell really directly from the observation whether you're seeing a brown dwarf kind of in the plane of the sky, close to the plane of the sky, or a planet close to edge on. And because they had this expectation that they shouldn't be finding these planets, they convinced themselves that they were seeing a brown dwarf star binary fairly close on. And it was a bit unlikely because actually it has to be surprisingly close to face on for it to work. But they sort of convinced themselves. They do actually say somewhere in the paper, or it could be a large planet. So they do actually at least make, you know, say we might have found a planet. The extra thing that Michel and Queloz did is they also looked at the properties of the star. So they actually could measure how fast the star is rotating, because you can see one half of it. If the star's rotating, one half of it's coming towards you, the other half's going away from you. And so you can actually see what you end up seeing is a kind of a broadening of the lines. So instead of seeing the line wobbling, you see part of the line being shifted one way, part of it the other way. The net effect of that is you see a slightly broader line. So they could measure the rotation of the star, kind of the at least, but again, it's the same thing, right? Is it a star that's rotating in the plane of the sky, or is it rotating edge on? But they knew some of the properties of the star. You could just make observations of it, find out what kind of star it is. And we know how fast stars typically actually rotate that are of that type. So they have this measurement of this kind of one component of how fast the things are rotating. And it could be either a very fast rotating star that's sort of pole on, or it could be a relatively slowly rotating star that's edge on. But we know intrinsically how fast stars like this actually rotate. From that, you can figure out that actually this system is relatively close to edge on. So there's one more leap here, which is that as long as the star's axis of rotation is the same as the planet's axis of rotation, which for example it is pretty much in the solar system, the sun's rotating about kind of the same axis that the solar system is, then that actually tells you that the system has to be relatively close to edge on. And once you've got that, then you know you've found a planet. So that was the sort of the extra bit that I guess that is what really got them the Nobel Prize. Plus actually just the confidence to say we found something that no one expected to find.
So in the future, if one day we go and visit other systems and other planets and we can somehow do this, this particular Nobel Prize one would be a good one to visit, wouldn't it? It'd be like a historic one. It'd be like visiting for humanity. This was a historic site for us.
It probably, I mean, it's not the easiest one to get to because it is 50 light years away, and we now know about planets, you know, that are only a few light years away. So it's probably not the first one that would ever get visited. But yeah, when it becomes routine, it will become one of the stops on the tourist trail, I suspect. Because of course there could be other planets in this system, right? We've just seen this one fairly massive Jupiter-like planet very close to the star, which really wouldn't be very hospitable because it's going to be a gas giant and it's going to be very hot and very unpleasant. But who knows, there could be other planets further out in the solar system.
Father of modern cosmology, does that mean there's an older cosmology? Like where did old cosmology transition to modern cosmology?
I'm giving the transition time around the 1960s, which by the way is another important time for the epoch of Higgs and Kibble and Brout and Ongler and people. The discovery of the cosmic microwave background radiation, I think that kind of transformed the field from being one that was full of speculation and promise in solving Einstein's equations without really knowing what the background material was in the universe, to the first time we established that this radiation, this remnant of the hot Big Bang, that emerged when the first atoms were formed, say 400,000 years after the Big Bang, and then just propagated outwards for the next 3.8 billion years, that the detection of that in the 1960s, 1965 in fact, it was announced by Penzias and Wilson, that where they associated a temperature to this radiation, that I think is what you might call, I'm calling here, that it's kind of the start of modern cosmology. And Peebles was there. In fact, it's not very well known, but the paper by Penzias and Wilson, which is 1 page long, 1 page, there we are, busting a gut, writing all these long papers, 1 page paper, about the third or fourth line, having announced that they discovered this radiation, that they don't really know what it is, they say that in the preceding paper in the journal, which is Jim Peebles' paper with Didier and Radial and Wilkinson, they say they've come up with an explanation for what this could be. And it is, in fact, the microwave background radiation at a temperature of around, at the time, they say 3.5 Kelvin. So it's now seen as about 2.7 Kelvin, but that's okay. It was 3.5 plus or minus 0.1, so they were perfectly okay. But Peebles was there. And in fact, not only was he there, he's the one that actually, in the previous paper, the one that literally appears before it, which is a mind-blowing 4 pages long, so that's a huge paper by comparison, he's the one, along with his co-authors, who suggest that actually this remnant radiation is linked to the hot Big Bang, and that it's got these thermal properties. It's that, I think, which is really key, that you can pin down as being one of Peebles' main contributions here, that he recognizes the significance of the radiation as being linked to the early universe. And the second thing that he does, which I hadn't seen done before, he points out that because we now know the temperature of that radiation, and because we believe in the idea of general relativity, and we can understand how that radiation changes its temperature as the universe changes scale because it gets redshifted, it cools down as the universe expands. It means it's hotter earlier on. And so he's able to link the temperature you've got today to an estimate of what the amount of matter must be in the universe today, because he knows what it must be sort of around the time of nucleosynthesis. He's got a bound he can use. And by doing that, he actually, in this paper, without, I don't think, necessarily really realizing that they're saying there must be some sort of dark matter, he actually points out that the estimate for the amount of baryons, matter in the universe in terms of baryons, is actually lower than the critical matter amount that you need, that we see today. We believe the universe today is spatially flat. That means there's a critical amount of matter in there. And he said in his calculations, there's not enough. And in fact, the end of his first paper, the one that appears with Penzias and Wilson, comes up with ways of trying to increase the amount. But he was there. He was pointing out this connection between measurement of the radiation and the density of matter in the universe. And that's absolutely integral to the rest of cosmology, in fact. The man in the street probably hasn't heard of the lambda CDM model, but I think if you said the standard model of cosmology, that's what you would say Peebles was responsible for. The standard model of cosmology has various contributions to the overall energy budget. So before Peebles was around, we knew that there were baryons, right? But we didn't necessarily know how many. And Peebles began to put a bound on that from this paper. But then he made some even bigger contributions in some sense. The next thing he sort of realized was that, again, using the fact that you've got this cosmic microwave background that had been detected by Penzias and Wilson, he was aware of the fact that there's fluctuations to be expected in this cosmic microwave background. And he's the one, along with you, who actually was the first to fully do sort of numerical simulations of different types of cosmology and predict what the Doppler, the acoustic oscillations were that we see in the microwave background. Remember those peak structures that are big peaks and then they go down in the CMB? He was the first to numerically show what different cosmologies would predict. And so he, in amongst it, he showed what a flat universe would do. And that's the one that pretty much is observed by, first of all, by WMAP, and then by Planck. The initial anisotropies were demonstrated by Kobe. But the original work, solving the numerical codes to show roughly what they would look like, is from Peebles.
What made him good? Like, why is he good at this? What is it about him that all the other cosmologists haven't got?
I don't think anybody has his overview. He's very, very strong mathematically. He's developed the statistics that's used in much of the analysis of the CMB and of large-scale structure. When you're looking at correlations of different regions of the sky, he developed the techniques you need. More than that, and his ability to solve equations and do integrals and things, he's still there. He's 85, but he's still very active and really on the ball. He has this overview. He can see the bigger picture. He can see how a given calculation, a given observation tells you something about something else in the universe by extracting out from that small initial observation the sort of its impact on the whole of the background evolution. And to do that is not easy because there's so many balls in the air and he's able to juggle them all in the air. And I think that in many ways is his big skill.
Have you ever met him?
Oh yeah, I've met him many times at conferences. He's such a nice guy. He's one of these people that is always prepared to give you his time. If you're walking for dinner or having lunch, he asks really pertinent questions, and I've always found him to be somebody that is easy to get on with. That when he asks questions, he's very polite, but he's not afraid to tell you if he thinks you're wrong, which he's done to me a couple of times.
Professor, I know in cosmology there are kind of different camps and schools of thought. You know, people who like string theory and A, B, and C and all that. Is Peebles on your side or on the opposite side?
Peebles sits sort of above it all. I don't think he's worried about the camps, to be honest. He goes where the science tells him.
Really excited Neil because it's for lithium batteries, and so he's gone on a battery safari. Some of you know that Neil is a motorcyclist. He has an electric motorcycle.